Welcome to Trending Unpacked, the show where viral stories meet calm, curious analysis.
Today, we are focusing on an event that, well, it just captured global attention almost instantly. We're talking about a sudden and really dramatic volcanic eruption in Ethiopia.
Yeah, you couldn't miss it. It sent maps, satellite images, clips of molten rock just everywhere.
Flying across the internet.
Exactly. And if you were online at all this past week, you saw the drama. I mean, this trended not just because of the raw power of it, the geology, but because of the sheer volume of real-time, high-quality visual data that was circulating. And that, combined with a bit of scientific uncertainty, just fueled this immediate, intense speculation.
And people were asking some big questions.
Huge questions, far beyond just, is this dangerous? People were genuinely asking, is Africa actually splitting in half right now?
And that's the gap, right? The gap where speculation rushes in. So our mission today is to take all this circulating material, all the thermal images, the seismic data, everything you saw, and really unpack the actual hard science of what happened.
So we can contrast that reality with some of those wilder online theories.
Exactly. To give you a clear, reliable picture of what is truly happening on the ground in the East African Rift, and maybe most importantly, why it matters to how you understand our planet.
Okay, let's get into it. Before we even look at the eruption itself, we have to zoom out a bit. We need to understand the tectonic context.
We do.
We're talking about Ethiopia, and specifically a region that is home to one of the most powerful and, let's be honest, kind of terrifying geological forces out there.
Yeah.
The East African Rift System, people call it EARS.
Yeah, EARS is absolutely foundational to this whole story. This isn't just a place where volcanoes happen to be. It is, it's the textbook example of divergent plate boundaries.
So plates pulling apart.
You're literally witnessing a continent separating in real-time geological history.
Right.
The crucial sort of nugget here is that this system is one of the only places on Earth where a continent is actively splitting apart.
And trying to form, what, a new ocean?
Fundamentally, yes.
Yeah.
Trying to create a brand new ocean basin.
So we're dealing with three massive tectonic plates all pulling away from each other here. You've got the Arabian plate and then the two big parts of the African plate, the Nubian and the Somali plates.
Right. And where all three of those meet and pull away, that's called the Afar Triple Junction.
That sounds like it would create just immense perpetual strain on the crust.
Immense is the right word. Because you have the Arabian plate sort of rotating and the other two pulling apart linearly, the crust in that region is just stretched incredibly thin, like taffy.
Okay.
And that tension is what explains why we see these specific, highly active volcanic regions in Ethiopia. You've got Erta Ala, which is famous for its lava lake.
Right, the persistent one.
Then Dello, with those surreal acid springs. And, very relevant to the current activity, Mount Fentel. They're all basically pressure release valves for a continent going through a very, very slow geologic divorce.
A slow divorce. I like that. But I know the tension itself is slow, right? We're talking millimeters per year.
That's right.
But when that release finally happened, I'm actually looking at, because I think when people hear catastrophic eruption, they picture a Mount St. Helens, that iconic cone shape. Is that the kind of danger we're talking about here?
It is not. And this is probably the most critical distinction we need to make to separate the fear from the facts.
Yeah.
The typical eruption style for this region, because of that stretched crest, is what we call a fissure eruption.
A fissure eruption, so not a single point.
No, not a central cone. We are looking at long cracks or ruptures in the ground, sometimes kilometers long, where lava just sort of emerges rather than being explosively ejected from one spot.
So the way the crust is built thin and pulling apart, that directly controls how the magma behaves when it comes up.
It determines everything.
And that behavior is mostly lava flowing out, not a giant blast. Why is that?
It really comes down to chemistry. Specifically, the type of magma you get in these rift zones. The magma rising here is overwhelmingly basaltic. That means it's high in iron and magnesium, and crucially, it's low in silica.
And high silica is what makes magma thick and sticky, right? Traps all the gas.
Exactly. High silica content makes magma viscous, sticky. It traps gases until the pressure builds up to a critical point. That's the shaken champagne bottle effect you see in volcanoes like Pinatubo or St. Helens.
But because the magma here in the rift is low in silica?
It's highly fluid, it's runny, it flows really easily, and this allows all the volcanic gases, water vapor, carbon dioxide, to escape relatively gently as the magma rises.
So when it hits the surface through one of those fissures, it just pours out.
It pours out, almost like an overflowing pot of soup.
Yeah.
It creates these massive lava flows that can travel for long distances, but you don't get those colossal high-altitude explosive plumes.
Visually dramatic, for sure.
Oh, absolutely. But generally, a lower hazard in terms of immediate blast damage or, massive atmospheric disruption.
That makes a huge difference in understanding this. Okay, so let's get to the timeline of this specific event. These huge pressure releases don't just happen out of the blue, right? Even if it seems sudden to us watching it go viral.
No, there are warning signs.
What were the scientists seeing in the days before the ground started to crack open?
Well, our sources confirm that there were several days of what we call precursor activity. It began with seismic swarms.
Which are what exactly? A bunch of small earthquakes?
Yeah, continuous clusters of small to medium-sized earthquakes. They're the geological signature of magma pushing its way up into the brittle upper crust. You're basically hearing the rock crack as the magma forces its way through.
So the trigger wasn't just magma moving, it was the speed and pressure of that magma creating a physical intrusion. I've heard the term dike used. What is that in this context?
The dike is essentially a massive, sheet-like vertical intrusion of magma. So try to imagine a giant molten wall pushing its way up through the cracks in the crust. And as this magma wall, this dike, ascends quickly, sometimes moving several kilometers a day, it forces the ground above it to swell and deform. That's the critical mechanism. The dike doesn't just rise. It acts like a giant wedge, splitting the continent from below.
And the visible event, the thing that everyone saw on social media, was just the moment that dike's pressure was too much for the surface rock to handle.
Precisely. The pressure exceeds the strength of the rock, large cracks appear, and you get lava effusion, that outpouring of runny basaltic lava. And, depending on how quickly the gases escape, you might see some small, localized ash plumes, but the main event is massive lava flows.
Okay, let's talk about the data, because that's what everyone saw. How are scientists actually monitoring this in real time? I mean, these are often very remote, hard-to-reach places.
They are.
We all saw those strange, colorful maps showing the ground deforming. How do they do that?
This is where modern science just transforms our ability to watch these events. Scientists track this almost exclusively with satellite technology, specifically something called INSAR, Interferometric Synthetic Aperture Radar. It is the absolute cornerstone of monitoring a rift like this.
You called it a super precise measuring tape from space before. Can you give us the quick technical version? How does a radar measure the ground in millimeters from orbit?
It's all about measuring something called phase shifts. The satellite's radar sends a signal down to Earth and records the exact timing and phase of the wave that bounces back.
Okay.
Then it passes over again a few days later and takes another image. Scientists compare the two wave patterns. If the ground has moved, even just a fraction of a centimeter, the phase of that returning radar wave will have shifted slightly.
Ah, I see.
So by merging those two images, they create what's called an interferogram. That's the colorful map you see. Each band of color represents a very precise amount of uplift or subsidence.
So those rainbow-colored bands aren't just an artist's impression.
Not at all.
They are the hard data confirming that a magma dike is literally inflating the ground from below.
Absolutely. And when you combine that with satellite imagery showing thermal hotspots, an unusual amount of heat,
it's direct confirmation.
The combination is undeniable. The hotspots confirm molten rock is at or near the surface, and the INSAR data confirms the ground is deforming in exactly the way you'd expect when a dike is moving underneath.
And the authorities on the ground are using this.
Constantly. Ethiopian geological authorities and international research partners are using this exact data to update their hazard assessments. This entire event, as vigorous as it is a highly monitored textbook example of the forces at play in the East African Rift.
Let's turn to the immediate impacts, because even if an event isn't explosive, it still affects people living nearby. What did the local reports say right after the fissures opened?
The initial reports, coming through news outlets and local authorities, indicated that while the event was definitely disruptive, the main concern was displacement, not immediate casualties.
So getting people out of the way.
Exactly. Villages experienced those initial light tremors, the seismic swarms we talked about, and that prompted temporary evacuations. The goal was to get people out of the direct path of any potential lava flows.
And what about infrastructure? It's a growing region. What's most at risk from these huge flowing rivers of lava?
Lava flows are slow, but they are completely unstoppable. They destroy everything. In this region, you're talking about essential transport routes, which are often quite limited.
Roads, bridges,
power lines, and perhaps most critically in such a dry region, irrigation canals or pump stations that support what little agricultural land there is. The news outlets really emphasize that while confirmed casualties were minimal, the real existential risk is the lava flow's direction. It can render farmland permanently useless and cut entire communities off from services.
And what about the bigger picture? Aviation, is that a concern here?
Aviation is always a concern with any eruption. Now, we did say this magma is more fluid and less ash producing.
Right.
But those localized ash plumes still pose a risk. If wind shear pushes them towards established flight paths, that's a problem. The ash is highly abrasive.
So constant communication is key.
It is. But the good news here is that the low explosivity tends to keep any ash plumes lower in the atmosphere, which makes them somewhat less hazardous than the massive high-altitude clouds you get from the big explosive volcanoes.
So to just quickly summarize the science part of this, we're looking at a highly monitored, predictable type of event, a vigorous fissure eruption driven by the continent stretching. And the main risk is the volume and direction of the lava, not a global catastrophe.
That is the factual summary.
Yes.
The dynamics of the rift are very well understood, and the current activity fits those established patterns perfectly.
Okay. Now let's pivot. Let's go from the cold, hard science to the viral narratives that took over.
The fun part.
Right. As we said, international attention just surged because these real-time satellite images, these dramatic maps, clips of lava, they spread incredibly fast on platforms like TikTok and X, and they often outpaced the more, nuanced scientific explanation.
And that gap between the visceral visual drama and the sober scientific explanation, that's the perfect breeding ground for sensationalism.
Yeah.
Uncertainty, combined with the spectacular nature of geology, just means the most extreme explanation often gets the most shares.
And the most widespread claim, the one that was in every single comment section, was what I'm calling the Great Continental Exaggeration.
Oh, I like that.
The idea that Africa is splitting in half overnight, or that the rift had suddenly torn open a gaping canyon.
That claim went truly viral. And it's a fundamental misunderstanding of timescale. Geologists have been monitoring this rift for decades. The entire process of a continent separating is an ancient, immensely slow geological process.
We're talking millions of years.
Tens of millions of years. When people see a surface fissure open up, their human sense of time compresses 50 million years of plate movement into a single catastrophic moment.
And the data backs up that slow view, right? We mentioned the spreading rate earlier, something like 6 to 7 millimeters per year in some parts of the rift.
That's right.
Can you put that in context for us? How does that compare to, say, the mid-Atlantic ridge where the ocean floor is spreading?
That's a great comparison. The mid-Atlantic ridge, where new oceanic crust is actively being formed, spreads at a rate of roughly 25 millimeters per year. Sometimes even faster.
So much faster.
Significantly faster. The EARS rate of 6 to 7 millimeters is much slower. And that difference tells us that the continental crust is thicker, it's more resistive, and that makes the whole rifting process much more drawn out and episodic. We're not watching an ocean suddenly appear.
You'd have to wait a while.
You would indeed need to wait about 50 million years for a true new ocean basin to form there.
So the fissures we're seeing now are literally just surface cracks. They're letting some magma leak out. They are not a sign that the entire continent has just cleaved open.
Not at all. The visual interpretation is just completely divorced from the geologic reality. The eruption is a symptom of the splitting that has been going on for eons, not the event that finished the job.
Another powerful narrative that always seems to pop up during big natural events is linking them to other global crises. In this case, there was a lot of online chatter attributing this volcanic activity to climate change.
Yes, the online assumption was that, volcanic activity might be on the rise because of shifts in climate. The reasoning you often see involves the idea of crustal loading and unloading.
What does that mean?
For instance, the idea that as massive ice caps melt quickly, the pressure on the crust underneath is relieved.
Yeah.
And that could, in theory, influence volcanic and seismic activity.
On a basic level, that sounds kind of plausible. Pressure changes, rock stability. But what's the real geological argument against that, especially for this eruption?
The crucial nuance here is that the current geological data does not support this connection for this event. The forces driving the East African rift are deep-seated. They're driven by huge mantle plumes, massive upwellings of hot rock from the Earth's interior, and the constant, inexorable pull of tectonic plates.
So forces that operate on a totally different scale.
A geologic timescale, millions of years. So even if rapid ice melt could potentially influence volcanism somewhere else, that mechanism is just dwarfed by the massive long-term tectonic forces at play in Ethiopia. The EARS process is fundamentally independent of our current climate cycles.
The timing is just a coincidence.
Scientifically speaking, based on the evidence we have, yes. It's coincidental in the context of plate motion.
And then, of course, we get into the really catastrophic narratives, the doomsday prediction.
Which you can understand. The sheer visual nature of it. Molten rock, the ground literally ripping apart. It's terrifying.
And that fed videos and posts speculating about massive continental fractures leading to immediate societal collapse.
And a major issue here was the misinterpretation of the visual data itself. Those precise scientific maps we talked about, the NATHA thermal maps, the INSAR deformation data, they were stripped of all context.
Right.
And they were treated online as end-of-world maps, where a thermal hotspot was assumed to mean a widespread, immediate rupture, not just a localized bit of heat.
I can see that. If you don't know what you're looking at, a map full of colorful, wavy lines looks like imminent doom. It's scientific accuracy being turned into high-velocity misinformation.
It's the ultimate example of how high-quality data requires high-quality interpretation. The fear gets amplified because the very tools that geologists use for prediction are misinterpreted by the public at signs of cataclysm.
And naturally, claims of conspiracy and secrecy followed. Any big, sudden event seems to spawn theories that the authorities knew more than they were telling us.
We saw claims of hidden government warning systems, allegations that major warning signs were deliberately concealed. This taps into a very human distrust of institutions,
A need to find someone to blame.
Exactly. Yeah. But the reality is that the scientific community was monitoring and reporting on the seismic swarms and the ground deformation in real time. The issue wasn't concealment. It was that a nuanced scientific warning like a magma dike is inflating, it just doesn't penetrate the public consciousness as quickly or dramatically as a simple viral video.
And there was also that element of comparative misdirection, right, where people were drawing parallels to eruptions in Iceland.
Yes, and that comparison is so seductive because Iceland is also a zone of active rifting and fissure volcanism.
It looks similar on the surface.
It does, but the comparisons were often misleading. Iceland sits on a mid-ocean ridge and a mantle hotspot. The crust is much thinner, the magmatic processes are different, the ears is continental rifting thicker crust, different chemistry.
Leading to a totally different hazard profile.
A completely different hazard profile. So drawing a direct parallel often dramatically overstated the potential for global ash dispersal or long-term aviation disruption based on what we've seen in Iceland.
So ultimately, all these viral interpretations seem to come from the fact that geology just operates on a timescale that is completely alien to our human experience.
Absolutely. The visuals are immediate and overwhelming, but the explanation requires patience and a knowledge of deep time. That ambiguity, combined with the visceral power of the imagery, just creates a sensational vacuum where these viral narratives thrive, easily outpacing the slower, sober, but ultimately accurate science.
So, having separated the slow, deep reality from the fast, viral fever, let's connect that high-tech data back to the ground reality and synthesize what we've actually learned here.
Okay. The geological facts are, at this point, crystal clear. The totality of what we've observed, the seismic swarms, the INSAR data showing ground deformation, the fissures opening, it's all perfectly consistent with the established tectonic stretching we expect in the East African rift system.
So this is a large, energetic version of a typical process, not some unprecedented cataclysm. But let me ask you this. What would alarm geologists right now? Even if this is a typical event, what specific data point would make them sit up and say, okay, this is different?
That's a key question. What would be alarming is a sudden, massive shift in the chemistry of the erupted lava. For instance, if it suddenly became highly silicic and viscous, that would indicate a completely different, much more explosive magma source.
That would be a game changer.
A huge game changer. Or if the INSAR data showed incredibly rapid, widespread uplift away from the immediate rift zone, that might suggest a massive, uncontrolled dike intrusion threatening populated areas far outside the known active zones.
But that's not what we're seeing.
No. Since the data shows consistent basaltic lava and localized dike movement right along the established rift, our analysis remains the same. This is typical, if vigorous, rift volcanism.
So the synthesis is that the actual data points to the continuous process of the continent splitting as the force driving these low explosivity, high effusion events. It's just the planet doing what the planet does in this particular spot.
Exactly. That movement hasn't stopped for 25 million years, and it's not going to stop now.
Okay, so when we strip away the doomsday scenarios, what are the realistic risks for people on the ground in the coming days and weeks?
The focus has to remain entirely on localized hazards. The primary concerns are tangible: disruption to transport and supply chains.
Roads being cut off.
Yes. The necessity of temporary displacement for communities. And the continuous need to monitor the direction of the lava flows to protect that limited infrastructure, like roads and irrigation canals. The localized risk from the lava is the hazard. The global risk of the continent splitting is a fiction.
And why should we expect this rift to just stay active? Is this going to happen again?
Yes. The activity is driven by the fact that the tectonic plates are still moving apart, and the deep mantle plumes continue to supply fresh magma to the thinning crust. The pressure never truly stops building.
So it's a constant process.
It is. Whenever a new batch of magma rises, a process we call magma recharge, it creates the potential for a new dike to form and new fissures to open. This is just the inherent persistent nature of living in an actively stretching continental zone.
Looking ahead then, what should we, the public, expect to see in terms of reporting and activity from the scientific community?
We should really emphasize the continued role of science and long-term monitoring. The immediate future will involve continuous scientific observation via INSAR and seismic networks. And because this is a fissure eruption, the activity itself could continue for a while.
Days, weeks,
maybe even months, with sustained lava fusion and localized ash plumes as the magma finds all the available paths to the surface along that rift zone. It's an extended process of geological pressure release.
Finally, let's just reflect on why this particular event trended so fast and so hard. The power of the geological imagery. We've seen volcanoes erupt before. Why did this one capture the global imagination in real time?
I think it's a convergence of a few factors. First, just the inherent visual drama of basaltic lava and open fissures. The planet is literally tearing itself open. That is intensely compelling.
Can't look away.
You can't. Second, the fundamental uncertainty that these events introduce. That feeling of nature being completely unrestrained is an immediate attention grabber. But I think most significantly, it's the rare quality of the real-time objective satellite imagery that we have access to today.
We're not waiting for grainy photos anymore.
No, we are co-observing precise thermal and deformation data almost as it happens.
And that real-time accessibility transforms a remote geological incident into a front-page global event. It allows all of us to feel like we're directly witnessing science in action, even if we don't have the framework to interpret the data correctly.
It connects us to the power of the planet in a very immediate, visceral way. I think the lesson here is that our technology has moved faster than our general scientific literacy, and that makes events like this instantly viral, even when the underlying process is slow, predictable, and strictly localized.
And there we have it. We've moved from the viral shock to the scientific reality of the East African rift system. And while the visuals of these geological events are, stunning and terrifying, understanding the underlying science, the slow, steady pull of tectonic plates, the specific chemistry of the magma, it really does allow for a much clearer and, crucially, a less panicked view of what's actually happening on the ground.
The planet's geological processes are just so vast and slow, they far exceed our immediate comprehension of time, but their manifestations, the eruptions, are immediate and spectacular. Learning to differentiate between those two timescales is absolutely essential to staying well-informed.
Next time, we're unpacking Black Friday 2025, the trends, the chaos, and why this year's deals sparked some unexpected controversy. Stay tuned.